of a weak acid and its conjugate base, or a weak base and its conjugate acid. And we talked about how these buffer solutions will resist changes in pH, right? And then we proved that by doing a bunch of calculations, okay? So we were talking about combining a buffer with, let's say, a strong acid. So we're going to continue to talk about combining acids and bases. Okay, and our first topic here is actually not combining acids and bases, but just combining acids. What happens if we mix a strong acid and a weak acid? Come on. Okay, so let's get like a sample problem here. What we're going to do is we're going to combine 0.5 molar HCl and 0.5 molar what's called acetic acid, HC3H8O2. All right, so mixing these two acid solutions together. So first of all, we're going to take note here of our acid dissociation equation. Where now we have to consider the fact that both of these acids are reacting with our water in our solution to produce those hydronium ions, right? So first, we're going to look at the acid dissociation reaction that HCl has with water. Remember our acid dissociation reactions. It's always an acid plus water. All right, everybody's going to take a second and give me my products here. Whoa. Okay, remember my base accepts a proton, so it increases in number of hydrogens, increases in charge. My acid gets rid of that proton, donates that proton, so it goes down in number of hydrogens, goes down in charge. And what do we know about HCl? Strong acid. So then what about this reaction here? Does it favor the products or the reactants? It favors the products very strongly. So strongly, in fact, that we say that this reaction goes 100% to completion here. All right, this is our strong acid. Means that our dissociation reaction goes 100% to completion. All right, we're going to do the same game, but for our weak acid. And how do I know that this thing is a weak acid? Well, what is it not? A strong acid. So if it's not a strong acid, it's going to be a weak acid. All right, so remember that list of 6 strong acids. Anything not on that list is not a strong acid. It would be classified as a weak acid. All right, so let's do our compound formula. This would be propionic acid, actually. again, we're talking about an acid dissociation equation, so I'm producing hydronium. All right, my conjugate base here, I'm going to have to look at my acid formula. I'm going to decrease the number of hydrogens, so C3H8O2. And I got to decrease its charge. Boom. All right, does this reaction also go to completion for weak acids? No, these are, in fact, I should be good and not use my one directional arrow, but use my equilibrium arrows here. All right, these reactions do not go all the way to completion. In fact, these reactions typically favor the reactant side of this equation here. So not much of this reaction actually occurs when we put a weak acid into solution. Very little of it will dissociate into those hydronium ions. Now, that still has a big effect on pH, since pH is on that log scale, but nonetheless, for our weak acids, we want to make note, this reaction, and really we'd have to make sure by checking our equilibrium constant, but generally speaking, favors the reactants. So that if I'm measuring the pH of my solution, I'm really measuring the concentration of what? What does the pH tell us? Concentration of hydronium, right? pH is just a restatement of that concentration of hydronium. So which one of these two is going to contribute to that hydronium ion concentration more? My strong acid or my weak acid? My strong acid, right? Because 100% of these are going to dissociate. All right. So when we do our pH calculation, what we're going to do is first calculate the contribution to our pH from that strong acid. All right, given what we've discussed about strong acids up until this point and calculating pHs of strong acid solutions, I want everybody to take a minute and calculate the pH of that 0.5 molar HCl. All right, so how do we go about doing this? We know that our strong acid concentration is 0.5 molar. That's from our problem here. And what we know about strong acids is that that concentration of my strong acid that I have initially will simply be equal to the hydronium ion concentration once that reaction goes to completion or reaches equilibrium. All right, so that means my equilibrium concentration of those hydronium ions is that 0.5 molar. In order to calculate my pH, I'm going to take the negative log of that 0.5 molar. So my pH here would be 0.3. Okay, remember my 1 sig fig here, I should leave 1 decimal place. Sig figs of my concentration become decimal places. I am going to put a bunch of extra digits down here just to kind of prove a point. Okay, cool. So we have this mixture of a strong acid and a weak acid. We know the strong acid is going to be the main contributor here to our pH because that reaction goes all the way to completion, meaning that all of my hydrochloric acids are going to be converted into hydroniums. And we calculated the pH of that contribution using our strategy for calculating strong acids pH. So now next, we're going to do our weak base, weak acid. All right, although I realized real quick, and this isn't really a big deal at all, but just to be extra special good here, I realized I miscounted my hydrogens. This would be C3H5O2, would be our propionic acid. So I'm just going to be good and update that. And as we said, this is an equilibrium reaction here, right? So our strategy for calculating pHs of weak acids is to do our equilibrium problems. So we're going to need to take our chemical equation here. We're going to have to build that Ka expression. All right, and then how do we go about solving these equilibrium problems? What's our strategy? What do we build? An ice table. All right, my Ka are my products, that hydronium and that conjugate base over my reactant. And that's, I get to omit my water since that's that pure liquid. It's not going to appear in my balanced chemical equation, or it's not going to appear rather in my equilibrium expression. And then I'm going to build an ice table. All right, if I fill in this ice table, the I, my initial concentration, what's my initial concentration of the weak acid? That 0.5 molar that I got from my problem. What about my initial hydronium ion concentration? Do I have hydronium in this mixture of strong acid and weak acid? Where did that hydronium come from? The strong acid, because 100% of that strong acid dissociated. So yes, I'm also starting out with this 0.5 molar, and we're just going to make a note here that this is from our strong acid. All right, but prior to the dissociation of that weak acid, I don't have any of its conjugate base in there. That change box, we're going to use that variable x. My reactants decrease in concentration, whereas my products increase in concentration. And to get that E box, I'm going to sum it all up. So 0.5 minus x, 0.5 plus x, and x. okay? All right, so if we want to figure out how much hydronium we have at equilibrium total, we're going to have to take the amount that we got from our strong acid and add however much of this acid dissociation reaction occurs for our weak acid. So we're going to need to take these and plug them back into our equilibrium expression. And I'm going to need to go to, I got too many variables as is, but I know that equilibrium constant for this reaction. Where do I find that? That constants page, right? So we have that chart that has all those different Ka values. So we got to look it up for this specific acid. Again, this is propionic acid or propanoic acid, either one, but that's this guy here. 1.3 times 10 to the negative 5 is that equilibrium constant there. Okay, so setting this all up, 1.3 times 10 to the negative 5, that equals 0.5 plus x times that value of x, and 0.5 minus x. All right, now what we're going to see is that x is indeed really small, but I want to make a point here. So what I'm going to do is I'm going to do this the real way. I'm going to solve for my value of x. We could do a bunch of pain in the butt algebra rearranging this, or we could use our handy-dandy calculators, right? So we learned how to use our calculators to calculate these real x values, and so that's what I'm going to do. I'm going to go to my number solver here. I'm going to punch in my 1.3 times 10 to the negative 5 on one side of this equation. And then I'm going to punch in, once I get rid of all this crap. Okay, punch in 0.5 plus x times x divided by 0.5 minus x. I remember we got to enter some seed value here. Again, x is going to be a tiny number. Not much of this reaction is going to occur at all. I know that because my equilibrium constant is a tiny number here. So I'm just going to seed it with some tiny number, 0.001, and let the calculator do the hard work for me. All right, so that value of x that my calculator spits out here, x equals 0.000012999. All right, so now, and let's just note here, this was the real x using that solver. So now we need to calculate the pH of our combined solution here, right? The weak acid, or the strong acid plus the weak acid. Right? As we can note, our equilibrium value for our concentration of hydronium is my strong acid contribution, that 0.5 molar, as well as how much of this reaction occurred, that value of x here. All right, so I'm going to do the negative log of my 0.5 plus that value of x and my pH is 0.3010. All right, so let's compare our two values that we got here. We're going to compare, this is the pH for the strong acid alone. That's what we did first when we calculated that pH. All right, we got this 0.3010299 business. And then we did the pH for our strong plus weak. All right, and we got this pH value here. All right, and what do we note about these two pH values here? Are they super different? No, they're incredibly similar. In fact, you got to go all the way to the 5th decimal place before you see any difference between these two here. So in our mixture of strong acids and weak acids, the vast majority of the hydronium comes from that strong acid alone. All right, so we can get a pretty good approximation here by simply ignoring our weak acid. All right, that strong acid is going to dominate our pH here. We're going to get some contribution from our weak acid, but very minimal. I mean, look at how tiny of a value X is here. So in terms of our pH, we can get a really good approximation by ignoring the weak acid, right? Ignoring the weak in this calculation. Cool. All right, so that's what happens if we mix a strong acid and a weak acid. We get a similar story if we mix a strong acid and a weak base. A strong base and a weak base. So now we're going to mix, now we're actually going to be combining acids and bases, and we're going to see what happens when we mix a strong acid and a strong base. All right, so we're going to combine 0.5 molar HCl and 0.42 molar NaOH. Okay, and my question is, what is the pH? Okay, so we need our chemical equation here. This is not going to be a dissociation equation. This is going to be an acid-base reaction, right? Because when you combine hydrochloric acid and sodium hydroxide, they will react with one another in this solution. All right, so we need an acid-base reaction between hydrochloric acid and sodium hydroxide. All right, now before we move on here, this is something that we brought up last time. I emphasize this to my organic chemistry students even. What is the sodium doing in this reaction here? Nothing. It's what we call spectator ion. It's just floating around. Whenever I see those group 1 metals in an ionic compound in an aqueous solution, I'm like, get rid of it, replace it with a minus sign, right? Because the hydroxide is really my base in this reaction. Okay, given what we've discussed about acid-base reactions, about conjugate pairs, everybody's going to take a second, draw me the products of this reaction. right, so my conjugate base of hydrochloric acid is that chloride ion. And what's my conjugate acid going to be in this reaction? Water. H2O. Boom. Okay, so, and we sort of did this last time, but I just kind of want to emphasize, we've been using these ICE tables as a way to solve equilibrium problems. We can also use our ICE table to help us account for how much of a chemical reaction has occurred. And that's what I want to know. How much of this reaction has occurred when I mix these two things together? So again, our strategy here is going to be to build an ICE table. All right, I'm going to keep track of my concentration of HCl, my concentration of hydroxide, my chloride ion concentration. I'm also just going to, for bookkeeping purposes here, I'm going to keep track of how much water is formed in this reaction. All right, I'll give you a little bit of a hint. At the end, I'm also going to prove to you that it doesn't matter how much water is formed in this reaction. Okay, but for right now, just for keeping track of how much of our reaction has occurred, we're going to keep track of all 4 of these components here. Okay, I started out with 0.5 molar HCl and 0.42 molar NaOH, and I don't have any reaction that's occurred yet. I'm going to use that variable X. My reactants decrease, my products increase. All right. And then finally, to get that E-box, I'm going to sum everything up. So 0.50 minus X, 0.42 minus X, X and X. All right, and now we're going to add that extra row, make an ICES table, where we'll solve for the equilibrium value of each of these compounds here. Okay. Cool. So when we started talking about these acid-base reactions, when we were talking about buffers, we said this very important principle that we're going to see over and over again in this lecture, which is that all of that strong will react. Right? But if we look carefully here, how much of this reaction is going to occur? What's our value of X going to be? All right, I have 0.5 moles of HCl, but I only have 0.42 moles of my base. Can all 0.5 moles of that HCl react? No. All right, and why not? Because I'm limited by the amount of hydroxide that I have. Right? Last semester we would have talked about limiting reactants. This is my limiting reactant here. So all the strong that can react will react. Every bit of this strong base will react. But importantly, I'm going to be left with some of that strong acid when this is all over. All right? So since I have my hydroxide as my limiting reactant, that means I know there's going to be none of it left over here. Right? All that strong will react. Which means what's my value of X? If 0.42 minus X equals 0, X must be equal to 0.42. All right, so then everybody take a second, fill in our other solve box here. So 0.5 minus x would be 0.08, x 0.42, x 0.42. So once I've mixed these two things together and that reaction has come to equilibrium, I don't have any hydroxide left over. I get a mixture of my HCl, my chloride ions, and my water. Okay? Now I asked you what the pH of this solution was. So out of these three here, hydrochloric acid, chloride, and water, which one do I not care about in terms of my pH? The water. And why don't I care about water? Because it's neutral. Water is not going to contribute to the hydronium ion concentration. Likewise, our chloride ions, we said that the conjugate base of anything strong was itself neutral. So both of these here, I can figure out how much I made. That's perfectly fine. I absolutely made these 0.42 molars. However, I don't care in terms of calculating my pH how much I made because they don't contribute. So really what I'm left with here is a solution that contains 0.08 molar HCl. Can we calculate the pH of a solution that contains 0.08 molar HCl? How are we going to do it? Negative log of our concentration, because if it's 0.08 molar HCl, all of that HCl dissociates. So we're left with this solution of strong acid. We're going to calculate our pH using our strategy for our solution of strong acid. All right, what remains is simply a solution of strong acid. All right, so my concentration of my HCl is simply equal to the hydronium ion concentration. Right, all of that HCl will dissociate. So in order to do the pH, I'm going to do the negative log of that 0.08 molar. All right. When we're using our ice tables, I'm not going to be too strict about keeping track of sig figs. We're just going to say about 3 decimal places. Boom. All right, so we combined our strong acid HCl and our strong base NaOH. We are trying to calculate the pH, and importantly, we're going to have the same principle we're going to use all throughout the day. All of our strong will react. Well, in this case, they're both strong, so I'm going to be limited by one of them, my limiting reactant. All of that limiting reactant will get consumed, and I'll be left with a little bit left over of whatever my excess reactant was. All right, so in this case here, I had to account for how much acid-base reaction occurred. And then what I'm left with is just a solution of strong acid. So I calculate its pH using our strong acid pH calculation. If I had started out instead with more hydroxide than HCl, then at equilibrium, I'd be left with a solution of strong base, and I would do my pH calculation for a solution of strong base. Okay? All right, so that's strong and strong. What about a strong base with a weak acid? I'm going to combine 0.25 molar NaOH and 0.6 molar of a weak acid. All right, let's grab one that we haven't used before. We'll do formic acid, great. HCHO2, 1.8 times 10 to the negative 4. What did I just say, 1.8 times 10 to the negative 4? All right, and as always, the question is, what is the pH? All right, so step one, we have to do our acid-base reaction. All right, given what we've discussed about acid-base reactions up until this point, everybody's going to give me a balanced chemical equation for our reaction between this acid and this base. All right, so I'm going to get my conjugate base, that formate, and my conjugate acid is water. And now I have to figure out how much of this acid-base reaction has occurred. What do we use to figure out how much reaction has occurred? Ice table. So everybody's going to take a second and build me an ice table. All right, and given what we discussed last time, I want you to try to solve that ice table. Get all the way to figuring out what that value of x would be. Uh, 0.25 for the base, 0.6 for the acid. So how are we going to go about solving our ice table here? All right, what do we know about this reaction here? What are we going to chant to ourselves for these problems? All that strong will react, right? That's just a fancy way of saying, or another way of saying, these reactions involving strong acids and bases will always go 100% to completion here, okay? So every little bit of that strong base is going to react with my weak acid, and since I'm limited by that strong base present in my solution, all of it's going to be consumed. All right, which means that my value of X has to be that 0.25 molar. So now I'm going to fill in all of my other boxes here by plugging in that value of X. I have 0.35 molar of that HCHO2, 0.25 molar of my conjugate base, and 0.25 molar water has been produced in this reaction. Okay? So if I look at my solution after I've done my acid-base reaction, after it's reached equilibrium here, I don't have any more of that strong base left over. That's all consumed. All right? If I'm talking about my pH, what else do I not care about up here? The water. Because again, water is neutral. All right? Am I allowed to ignore my conjugate base? Okay, so be careful. We were able to do that last time because both my acid and my base were strong, meaning that their conjugates were both neutral. All right, remember we talked about this inverse relationship between acid strength and the strength of its conjugate base. The conjugate of something strong is always neutral, but the conjugate of a weak acid is itself a weak base. Right? So no, we cannot ignore the presence of that weak base in our solution. All right, so what we're going to make note of here is we have this mixture of a weak acid and its conjugate base. And we're trying to figure out the pH of this solution. But wait, we have a special name for mixtures of weak acids and their conjugate bases. What are those? A buffer. And so what we've just done is we've created a buffer solution. And I think I heard some sighs of relief out there. That's because if we do have a buffer solution, in order to calculate our pH, we just get to use that Henderson-Hasselbalch equation, right? That equation that only works for buffers, but since what I've created here is a mix of a weak acid and its conjugate base, I've created a buffer. Check, check. We can calculate our pH. Using that buffer solution approach. All right, so this is this Henderson-Hasselbalch equation. My pH equals my pKa plus the log of base over acid. All right, so everybody's going to take a second. Given we looked up our Ka before, 1.8 times 10 to the negative 4. Take a minute and calculate the pH of this solution. right, so remember the pKa, just like pH is the negative log of the concentration of hydronium, pKa is just the negative log of that Ka value that we looked up on our constants page. And now I need to do the log of the concentration of base divided by concentration of acid. Importantly, which one of these is my base here? The 0.35 or the 0.25? Right? Looking carefully at our formulas here, this is my acid, this is its conjugate base. So that 0.25 goes in the numerator, at 0.35 in the denominator. All right, so punch that into my calculator. We get 3.599. We'll just do 3 sig to our 3 decimal places. Okay. Cool. So we did our strong base with a weak acid. Our strong base was limiting here, so all of that got used up in this reaction, leaving us with a mixture of that weak acid and its conjugate base, what we call a buffer solution. So when we went to calculate our pH, we used our Henderson-Hasselbalch equation that we can use for buffer solutions. Okay? I'm going to keep these same examples just for the sake, same compounds, just for the sake of simplicity. We don't have to redo our balanced chemical equation. All right, but now we're going to do this same question here. But now my limiting reactant is not going to be my weak acid, so I'm going to change these amounts. I'm going to use 0.6 molar NaOH and my 0.25 molar of my weak acid, right? So I'm going to switch these around. I want everyone to take a second and see if you can't calculate the pH of this solution. Again, this reaction is going to go 100% to completion, but now I'm limited by the amount of weak acid that I have in that solution, right? My weak acid is going to be consumed first. That looks about right. 3.599. right, this reaction again is going to go 100% to completion, but now my limiting reactant here is that weak acid. So all of that weak acid is going to be consumed, meaning my value of X is that 0.25. So when this reaction reaches equilibrium, I'll be left with 0.35 molar hydroxide, 0.25 molar conjugate base, and 0.25 molar of water that's been created. And if I'm asking about calculating my pH, which one of these do I not care about? Neutral waters. First of all, I don't have any of my weak acid left over. I don't care about my water that's been created because it's neutral. All right, so let's just say we can ignore the neutral. All right, so what I'm left with here is a mixture of these two components. My hydroxide is what? What do we know about hydroxide? That's a strong base. And what about the CHO2 minus? Yeah, so it doesn't have a donatable proton. It's the conjugate base of my weak acid. So we have a mixture of a strong base and a weak base. And we could kind of do it the long way, just like we did at the beginning of our lecture here today. But what did we say about a mixture of a strong and a weak? What do we get to do? I mean, it sounds kind of mean, but we're going to ignore the weak, right? We could go and account for it. It just doesn't have a large contribution to that, in this case, hydroxide concentration compared to my strong base. So we're going to use our ignore the weak rule. All right, to be clear, that's because we have not a mixture of a weak acid and a weak base, which was what we were left with before. We did not ignore it, right? But because it's a mixture of a strong base and a weak base, yeah, we get to just ignore the contribution of the weak base. So then everybody's going to take a second, based on what we did before, calculate the pH of this strong base solution. All right, so I'm going to take the negative log of that 0.35 molar, giving me 0.455, or we'll round it off to 0.456, and I'm done. No, okay, because what did we just calculate here? We got to be careful. The POH, awesome. So in order to convert, since we're talking about a basic solution, but we want to talk in terms of pH, we're going to have to use that auto-ionization relationship that says that pH plus POH equals 14. Or I can rearrange this. My pH is going to be 14 minus my POH. All right, and that leaves me with a solution with a pH equals to 13.544. So let's just summarize here. We were talking about a strong base, weak acid combo. And what we just did were two different calculations that ended up in slightly different results here. All right? When we had that excess of our weak acid, aka that strong base was limiting, that's when we were left with a buffer solution. If instead we had an excess of our strong base and our weak acid was limiting, then once that reaction is all done, I'm left with simply a strong base solution. Cool. All right, so we're going to do one more here. This is now last situation I'm going to throw at you is what if we have a strong acid and a weak base? All right, we're going to combine 0.36 molar, we'll use a different strong acid. Let's use HBr. And we're going to do 0.79 molar ammonia. All right, ammonia is going to be a weak base. So let's go to our constants page here. We're going to grab that Kb value. Now it's a Kb value, not a Ka. For ammonia, 1.76 times 10 to the negative 5. So that's our weak base. Where are we? Okay, and of course, like always, we want to calculate the pH of the solution. All right, so given what we've discussed up until this point, I believe in y'all. You're going to give me our acid-base reaction. Then you're going to tell me how much of this reaction has occurred using an ice table. All right, I'm going to give you a little bit of a head start, and then I'm going to quietly fill in up here, and then we'll go about figuring out how we use that information from our ice table to calculate the pH of the solution. Okay, so now in this case here, again, all this strong will react, meaning this reaction is going to go all the way to completion here, but I'm limited by that amount of hydrobromic acid that I have, meaning that all of that will be consumed, or that value of X has to be 0.36. And then I'm going to take this and I'm going to plug it all into my calculator here to solve for my other boxes. So 0.79 minus that 0.36 gives me 0.40. 0.3, I messed that up, 79, 43. 0.36 and 0.36 for my X. All right, so now we have successfully accounted for how much of our acid-base reaction has occurred. I was limited by my HBr, so I don't have any of that. What else do I get to ignore up here that I have in my solution in terms of my pH calculation? Bromide. Why do I get to ignore the bromide? Because it's the conjugate of something strong. The conjugate of something strong is always neutral, right? So we're going to ignore the neutral. Unlike water, which I think we all know, I have a sense, is neutral just because, you know, we're alive. We got to remember for our other strong acids and bases, we get to, their conjugates are neutral. So ignore neutral. We're going to just make note, it's the conjugate of a strong. Cool, so now I'm left with a mixture of this weak base and its conjugate acid. And we have a special name for mixtures of weak bases and their conjugate acid. What am I left with here? Another buffer solution. All right, and so for buffers, we get to use this Henderson-Hasselbalch equation. Our pKa, pH equals the pKa plus the log of our base over the concentration of acid. Okay, but I have a problem here. All right, what's my problem? It's a base, so I don't have a Ka, I have a what? I have a Kb. That's what we looked up on our table here, was the Kb of ammonia. All right, but remember we discussed this relationship between the Ka of a weak acid and the Kb of its conjugate base, or vice versa. All right, these are both related where the product is always going to be that Kw, and we know Kw is 10 to the negative 14, right? So they're always going to be equal to that same 10 to the negative 14. So even though I have a Kb, I can find the Ka of this buffer system. I just need to use this relationship here in order to do it. Okay? So, going to our, everybody take a second, given what we've discussed here, see if you can't calculate the pH of this solution. Which one of these is, if I'm going to do my ratio of base to acid, which one of these is my base, the ammonia or the ammonium? The ammonia is my base. This would be its conjugate acid. So that 0.43 needs to go in the numerator, 0.36 in the denominator. All right. Punching this into my calculator, I get a pH of 9.323. All right. One thing I just want to caution on, when you're doing this calculation here, in your calculator, you need to put that numerator in the denominator in parentheses to make sure to keep your order of operations correct. Right? Otherwise, you'll divide by the 1.76, but end up multiplying by the 10 to the negative 5. What's up?
What if I just like find the pOH and subtract it from 15?
You can. There is a different, so this is a good question. There's like a different, almost equivalent version of this that we could frame in terms of pOH and pKb. But importantly, this is what I'm going to give you as the formula on the exam. So if you want to use that other way, great. That's all on you. But importantly, this is kind of the tool you're given on your exam. What's up?
What day do you start?
It's not next week, but the week after on Monday and Tuesday. The exam schedule and the syllabus and everything has been updated. So you can go and find that information there.